Well, good afternoon, everyone, and a warm welcome. No, it's still morning. Good morning, everyone. A warm welcome to the first of our special lectures that are attached to the Ways of Knowing course, which all first-year students are taking here. I'm Sue Sorensen, and I teach English, and I'm also one of the Ways of Knowing instructors. And I think most of them are around. I'll just get them to wave. I see Karen and Delmar and Andrew, and Paul is at the back. And Kenton is probably still serving food. So that's the 6 of us who have been teaching individual sections, and then every 2 weeks we get together in 2 big groups of about 90 and have a roundtable. And this is everybody today, about 180 plus other people from the university, because this is an open public lecture for anyone and everyone. So now the Ways of Knowing students will have been through this cycle once, and we'll do it again in October, and we'll do it again in November. And at the end of the course, there's going to be a fabulous symposium. And for those of you that saw it last year, it was really something. So, and students will do all sorts of projects of their own devising. And our subject this year is hope. I want to say that I'm a guest here myself on Treaty 1 territory, and I'm very grateful for the many peoples of the past and the present who have stewarded this place and continue to take care of this beautiful land. I'm going to introduce Candice Viddal very briefly, and then afterwards, after Candice does her lecture, then there'll be a short time for Q&A. But Dr. Candice Viddal, I think, has been here for a little over 10 years, teaching both chemistry and physics, and she's very passionate about both. And indeed, people have noticed her passion in teaching because I believe last year, yes, in 2023, she was one of the recipients of the Kay and Lauren Dick Award for Teaching Excellence. So Candice loves teaching, and she loves her students. I have to read this sentence. Her research is on the structure, function, and dynamics of proteins, with a particular interest in applications in human health and the environment. In her spare time, Candice is able to both play the piano and the saxophone, and she's also a poet, a published poet. And Candice promises us that there will be no equations in this lecture. So please welcome Dr. Candice Viddal.
Good morning, and thank you, Sue, for the very kind introduction. This year's Ways of Knowing course is exploring the topic of hope. Now, when I was asked to give this lecture on hope, my first thought was, where do I begin on such a broad topic such as this? But as I continued to think about it, I kept returning to the broad sense of hope I feel when I do science. The joy it brings to pay close attention to the workings of nature, but also when I reflect on how knowledge about the world was able to affect positive change in the past, and how new discoveries bring hope for positive change in the future, both in our material circumstances and in our attitudes. So, in today's lecture, I will explore the idea that science brings hope. And as a physical scientist, I find hope in seeking to understand the physical nature of the universe, and with a belief that doing so is fruitful for human beings, for our societies, and for ourselves. In 2003, Bill Bryson, journalist and author, wrote a popular science book called The Short History of Nearly Everything, which he wrote to improve his own general science knowledge, claiming he had feelings of conceptual alienation from the physical world around him. He explained his dissatisfaction with a distant approach to scientific knowledge that characterized most science textbooks and science teaching at his school as a motivation for writing the book. And many of you may have experienced science courses as feeling cold and dispassionate and impersonal. However, the stories behind the science enrich the content. When we look at what the world was like before modern science, and when we learn about the scientists themselves, who lived and worked in a particular time and place, influenced by their cultures, with ideas, curiosities, and desires and beliefs, we get a better insight into why science is done, why it matters, and how it changes us. In what follows, I will reflect on the hope that scientists of the 17th century in Europe had for understanding nature and improving the world. And I will begin by giving you a sense about what life was like in Europe at this time. This is a time that scholars say marks the early modern scientific age, when the modern methods of science that we use today began to emerge. Then I will highlight the discoveries of two major figures from this time, Johannes Kepler and Isaac Newton, to give a glimpse into how scientific understanding is arrived at. At the end, I will briefly discuss how our human values interact with the creation and use of scientific knowledge, and I will draw on two scientists as examples, Lise Meitner and Ursula Franklin. Now, humans have always tried to understand nature, and many cultures around the world have produced knowledge that tried to make sense of what they saw around them. They also invented technical knowledge for making tools to make their lives easier. But the emergence of what we call modern science began in the 1600s in Europe. At this time, many scientists set out to discover natural laws that govern how the universe behaves, resulting in the most effective way humans have ever devised of understanding the natural world. Most effective in depth, breadth, and overall coherence. A process that follows reason, observation, and accurate measurement to find out how the world works. In other words, science is the process of sense-making and finding order out of chaos. Because to our sense impressions, the universe is a chaotic place from which humans have often felt alienated. We often experience ourselves as separate from the natural world, emotional beings at the center of things. But careful observation and rational thinking can shift our attention away from our inner selves to develop an understanding of natural processes. The scientific revolution that began in the 15th to 17th centuries emerged from a context of living in Europe that was very unstable. Life expectancy was around 35 years, and disease spread quickly. In London, England, for example, deaths outnumbered births at many times throughout the century. Hygiene was non-existent, and knowledge of germs was lacking. Bathing wasn't something most people did, and worms and insect infestations were experienced by nearly all. Religious wars were common, and society was marked by significant inequality. And superstitious ideas were prevalent because people understood very little about nature. Because of the lack of systematic medical knowledge, treatments used by physicians were questionable and often based on superstitious ideas and beliefs also. One example was that swallowing a spider could cure a fever. And some treatments made the situation worse. Also, in the night sky, the appearance of comets produced superstitious ideas. Comets inspired dread and fear because they didn't move in regular patterns like planets, and their appearance was often blamed for natural disasters and wars. Amidst the uncertainty and insecurity that characterized life at that time, an ever-growing group of natural philosophers were interested in building firmer knowledge of the natural world through a combination of empiricism and reason. That is, a combination of experience and observation alongside reason. The natural philosophers formed the Royal Society of England in 1660, and their motto was nullius in verba, which means take nobody's word for it. That is, they believed that knowledge should not be taken on authority alone. Knowledge of what and how is based on experiments and observation and should be subject to continuous revision and correction. The Society's primary aim was to encourage the exchange of ideas by scientists to enable scientific knowledge to be built in a collaborative way. And the Royal Society created the world's first scientific journal for this purpose, called Philosophical Transactions, a journal that is still in print today. Now, before I continue, I want to offer a note on terminology. The term natural philosophers is what was given to those who studied nature broadly, and that was the name used since ancient times. The term scientist did not come into use until the 19th century, but I will use the term scientist throughout this talk, even when referring to those that came before the 19th century. Okay, so the natural philosophers were interested in building firmer knowledge of the natural world through empiricism and rationalism. What I want to note here is that this was a big change in mindset, because the dominant way of knowledge creation prior to this involved verbal arguments rather than careful observation. The primary concern before was trying to explain why things happened. The aim of experimentation was to first get a good sense of what was happening in nature, and then to explain how it was happening. And the emphasis on the acquisition of knowledge through experimental investigation ultimately led to a rigorous scientific method. Scientists had a confidence and hope that approaching nature in this way would lead to, 1, a better understanding of nature, and 2, practical answers to some of humanity's biggest challenges so that they could improve their lives and make them longer and healthier. One of the earlier figures of the scientific revolution was Johannes Kepler, who lived before the formation of the Royal Society. Kepler was a German mathematician and astronomer, and through his work, he defended Copernicus's model of the universe, which had removed Earth from the center, as had been assumed for centuries, and replaced it by the sun. Now, Copernicus's model was a very controversial idea at the time. The belief that the Earth is in the center seems to make so much sense based on our experience, right? Imagine for a minute that we had no photos of the Earth from space. Imagine also if nobody ventured beyond the Earth's atmosphere to tell us about it or to take photos from their viewpoint. Imagine that and focus on looking only at what you can see and experience based on your own senses. It does not all feel like we are moving on a planet that is rotating, for one, and the suggestion that we are, without our current knowledge, seems to defy common sense. The sun moves from east to west, and the stars and the planets are in motion around us, while we appear to be stationary and still. So it is easy to imagine that it would take a lot of effort to convince somebody that this wasn't true. So the old geocentric picture of the universe seemed quite reasonable. But Kepler was able to demonstrate the accuracy of the Copernican model by painstakingly analyzing large amounts of extensive observational data of the positions of Mars that astronomer Tycho Brahe was able to obtain using telescopes. Now, when approaching the work, Kepler began with a mystical belief. This belief was that the orbits of the heavenly bodies around the sun would be circular. The circle had held meaning for ancient philosophers because the circle was a symbol of eternity and was considered the most beautiful of all the curves. However, after much effort trying to make the observational data fit a circle, Kepler eventually determined that the motion of Mars around the sun was an ellipse. This also matched the observation that the planets did not move in their orbits at a regular rate of motion, but that they moved faster when they were nearer the sun and slower when farther from it. And we can see this in the picture. It takes the same amount of time for a planet to cover the distance shown on the right as it does for a planet to move the much shorter distance shown on the left. Planets moving in circular orbits would move in a constant rate. This is one of Kepler's laws of planetary motion and is a model of the planetary orbits that comes from observational data. As a person, Kepler was motivated in his scientific work by his theological belief in an orderly cosmos, and to him, astronomy and the divine were one and the same. He saw participation in the discovery of knowledge as an observation of the goodness and wisdom of the Creator. He also spoke of the meaning he found in studying nature by saying, "When the storm rages and the shipwreck of the state threatens," he wrote, "we can do nothing more worthy than to sink the anchor of our peaceful studies into the ground of eternity." That quote reflects Kepler's personal experience of living in a very turbulent political time. There was a witch hunting hysteria that swept across Europe, and estimates are that between 40,000 and 100,000 women were executed over a span of the 300 years between 1400 and 1700. And in 1615, Kepler's mother, Katharina Kepler, was charged with witchcraft. Some examples of the evidence brought against her was, number one, that she appeared as a ghost through closed doors. Number two, that she caused paralysis of a schoolmaster from a drink of wine. And number three, that she caused excessive pain to a butcher when walking past his bench. The case against her took years, and by 1620, Katharina was imprisoned. Now, when an accused witch was brought to trial, severe torture was routinely used to get a confession. Furthermore, the accused was presumed guilty until proven innocent. And the finding of guilt resulted in execution, usually by hanging, drowning, or burning. However, Johannes was very dutiful. His family hired lawyers, and along with them, he took over the trial. He wrote a defense that has been described as a rhetorical masterpiece in which he used basic medical knowledge and common sense to explain away the charges brought against his mother. To the charge of causing pain to a butcher without touching him, Kepler wrote, "Daily experience shows that someone who has previously engaged in strong motions, as when a butcher chops meat, can easily develop a pain in his limb, which eventually abates." His ability to dissect the accusations against his mother in a scientific way resulted in her acquittal and release. But beyond practical uses, Kepler found studying nature to be a source of deep joy and contemplation. He said, "The diversity of the phenomena of nature is so great, and the treasures hidden in the heavens so rich, precisely in order that the human mind shall never be lacking in fresh nourishment." Later, in the century in which Kepler lived, there were two big threats to the people of London. The plague of 1665 saw the death toll in London rise to 6,000 a week by late summer of that year, with a quarter of the population being killed by the time it was over. Whole families would die in a single day. In a city of approximately 450,000 people, which is just over half of the size of today's Winnipeg, these are astounding numbers. And following the plague, immediately after, another disaster occurred. This time, it was a fire. It started in a bakery near London Bridge, but an apathetic response from the mayor followed by a gust of wind, soon had the flames spreading far and wide. What made matters worse was that London had been experiencing a drought that year. Its buildings were mostly constructed out of wood, and they were built so close together that the fire spread rapidly. There were many combustibles, such as oil and stacks of cloth in the warehouses and shops, that also contributed to the disaster. The piped water supply was cut off by the flames, leaving the creation of fire breaks by demolishing buildings with gunpowder explosions the only method that remained to fight the fire. The fire burned for 4 days before it weakened, leaving much of the city unrecognizable and leaving 13,000 homes and 87 churches destroyed, along with many warehouses. And as if the destruction itself wasn't bad enough, these events were not viewed by the people at the time as natural calamities as many of us would today. As terrible as the events were, the fear was not solely based on dealing with the event and its consequences at hand. People lived in even greater fear when these disasters occurred because they believed the plague and the fire were God's punishment for something they did, and they were worried that more was coming. However, scientific thinkers worked with the belief that there was order behind the chaos and that a careful study of nature would reveal regular patterns, providing a better understanding of nature. And it's knowledge of those regular patterns that would help us to shape our world. It was right around this time that Isaac Newton was living at his mother's farm in England, isolating from the plague. And he was thinking about a big question that persisted about planetary motion that had been described by Kepler. Kepler described how the planets moved, but Newton wanted to understand what caused the motion of the planets. That is, he wanted to understand what physical mechanism allowed them to revolve around the sun. What force allowed them to move in a circle rather than flying off in a straight line? Earlier thinking about motion, formulated by the ancient Greek philosopher Aristotle, was that the celestial bodies, such as the moon, the planets, and the stars, moved continuously by nature, but the motion by bodies on the earth terminated unless acted on by a force that would get them moving again. And the legend tells of the story of Newton sitting under a tree when an apple falls on his head, and he realizes the answer to this question he has about the planets. It occurred to him that the motion of the apple as it falls toward the earth is no different than the motion of the moon as it revolves around the sun. And in a thought experiment, he imagined a stone being projected from the top of a high mountain. At low launch speeds, the stone would just fall straight down to the earth, as we see in path A. At higher launch speeds, it would travel a bit farther before falling to the earth, as we see in path B. And at speeds much higher, it would travel in an elliptical path and orbit around the earth continuously, as we see in paths C and D. This is because of gravity, a force that the moon and the earth exert on each other that causes the moon to be pulled toward the earth rather than move in a straight line without hindrance. In the figure, marked by the large blue arrow pointing down, we see the path the moon would take without the presence of the earth. However, the gravitational force between the earth and the moon causes the moon to fall back to the earth. Now, using the known distance from the Earth to the moon and observations of the moon's position with time, Newton devised a mathematical expression that matches the observational data and is called the universal law of gravitation. This was also an explanation for how all of the planets stayed in their orbits around the sun. So what Newton showed was that the motion of all bodies, either terrestrial or celestial, were governed by the same laws, with gravity the force acting between them, and it revolutionized the way we understood the universe. That is, Kepler simply described the motion of the planets, but Newton provided an explanation of how they were moving that involved a physical force. And Newton carefully explained these ideas in his Principia. This book is widely recognized as one of the most important books in the development of modern science. His thought emphasized experimental observation combined with mathematical analysis that expanded what was possible for scientific study. Overall, the Principia described a standard for doing scientific investigations, which ultimately formed the foundation of the modern scientific method and ushered in a new era. As many knew, Newton's theory drew a lot of criticism. One of the reasons was that his model was so simple, and many expected a more complex description of the motions. The mysterious force of gravity, which permeated the entire universe and caused motion at large distances, also led to accusations that Newton was relying on magical ideas to describe nature. However, our understanding of Newton's laws made it possible to send astronauts to the moon. Newton's scientific work is a masterpiece of scientific thought, but Newton the person spent much more time thinking and writing about theology than about physics. He believed deeply that the order in the universe was a manifestation of the divine intelligence, and that science was a way to bridge the human and the divine worlds. To Newton, the existence of orderly mechanisms was both consistent with and a reflection of the nature of God. And in addition to Newton's physics, the Principia is interspersed with Newton's metaphysical and deep theological thinking about nature. Now, the methods of modern science used by people around the world have produced a significant amount of knowledge about the natural world in many different fields over the last 350 years. Because of the advances in scientific knowledge since then, our society has different standards of living. Diseases that are now understood much better are routinely vaccinated against. Births outnumber deaths. We now understand that washing our hands and sterilizing medical equipment prevents the transmission of diseases. We have effective insect management plans. And our medical knowledge in general is much more advanced. Comets are commonly referred to as dirty snowballs, and their trajectories in the sky are predictable. So we can schedule comet viewing events in advance for the large number of comets that we are aware of. So the process of doing science involves looking for objective, verifiable knowledge that systematically builds on itself. And the self-correcting nature of science helps us eliminate flawed conclusions about nature that we may have arrived at due to our own bias. And the scientific method, and one that was reflected in both Kepler and Newton's work, roughly follows the following steps. Number one, scientists will carefully observe a phenomenon or perform highly controlled experiments to learn more about it. Number two, from the observations, a hypothesis or law is formulated. This is a proposed explanation of the observations that is falsifiable. Falsifiable means that the explanation is expressed in such a way that it could be confirmed or denied by further experiments. Number three, for very well-established hypotheses, a scientific theory can be developed. This is a model that describes nature in some aspect, but also attempts to explain the behavior using other scientific concepts. Number four, theories are then tested with further observations. Each observation has the potential to refine or modify the original theory. Number five, all scientific theories are open to further experimentation and observation. They are never conclusively proven, but they can be very accurate models that persist over long periods of time and have a high degree of explanatory and predictive power. Number 6, theories that have been exhaustively tested through experiment are as close to an accurate model of nature as possible. In other words, the scientific method involves going from the particular to the general and back again to generate more knowledge. Really important step number 7, there is creativity required to construct a scientific theory. Scientists who create theories are guided by data, but also by a creative process that attempts to capture nature in an efficient and powerful way. Now, it is important to remember that scientists themselves, as people, can have just as much conviction about their own untested ideas and conclusions as anyone else. They come to their work with their own beliefs and attitudes and models of the aspect of nature they are studying, and they don't enjoy being told they are wrong any more than anyone else. Scientists are very often resistant to change. But what makes the scientific method so effective is that it is a social enterprise. The theories that persist over time are those that the scientific community find the most convincing based on their explanatory power and strength of evidence. Any conclusions that are arrived at, to be considered valid, must be testable and repeatable in the way I described. For example, when we, as scientists, submit a paper for publication, our work must be described in such a way that any other scientist with the same equipment and samples would be able to repeat the work and get similar results. The conclusions cannot and should not simply be taken on authority. In this way, the scientific method acts to enforce humility. Scientists, as a group, are only convinced that a particular theory or model is an effective descriptor of nature over time, with continuous experimentation and a high degree of reproducibility. Although a Nobel Prize winner might have a new way of looking at things over the course of their career, and give lectures on their ideas, and use verbal and descriptive argument to develop new ideas, simply being a Nobel Prize winner does not make their theories or ideas acceptable to the scientific community. The scientific process of evaluation and repeated testing is still required and works over time by an accumulation of contributions from many working in the field. So, in many ways, the scientific method is an expression of the hope that we can understand nature to a significant extent, and that the knowledge we gain from doing science helps us to overcome ignorance of nature and superstition about it. Scientist Lise Meitner said that science makes people reach selflessly for truth and objectivity. It teaches people to accept reality with wonder and admiration, not to mention the deep awe and joy that the natural order of things brings to the true scientist. Some scholars argue that the origins of modern scientific thought are rooted in its theological underpinnings. Physicist Peter Hodgson said, "The essential presuppositions of science, that matter is good, orderly, rational, contingent, and open to the human mind, are all to be found in the Old Testament." Contingent means that the way matter behaves is not a logical necessity. It could have been different. So to understand nature, experiments and observation are necessary because its behavior cannot be deduced from logic alone. In the Old Testament, seeking knowledge goes together with acquiring wisdom. For example, Proverbs 15, verse 14, speaks of a discerning heart as being one that seeks knowledge. There are also passages that illustrate how knowledge of nature helps us to form a beneficial relationship with it. For example, in Isaiah 28, there is a passage that describes agricultural methods using agricultural knowledge of the time. When a farmer plows for planting, does he plow continually? Does he keep on breaking up and working the soil? When he has leveled the surface, does he not sow caraway and scatter cumin? Rather than being a guidebook for farming, the point I'm trying to make about this passage is the implication that knowledge of nature is key to forming a fruitful relationship with the rest of creation, and that we must study nature carefully to acquire that useful knowledge. There are methods that will work and that will yield beneficial results, and there are methods that will be ineffective. Now, using scientific thinking does not mean we have to aim to be purely cerebral beings who only think scientifically. Far from it, nor would this be desirable or even possible. The scientific method was invented precisely because we can be mistaken about the workings of the world around us, and we often are. But being aware of our ability to leap to incorrect conclusions and filter through the subjective parts of ourselves to find reliable knowledge about nature can help us to make progress. We can bring scientific knowledge back to use for practical purposes, whether it be in engineering or medicine. And practical application of that knowledge can help us to improve our living situation and take care of our communities. And there is hope that new discoveries will improve our lives. This process in learning how to find a path to gaining practical knowledge has been a net benefit to the world. But science alone cannot tell us how the knowledge we gain should be used. It can and it does interact with what we believe about our own humanity and our place in the world, while also informing our beliefs. For example, a particular scientist's choice about what to study or how to approach a problem will be influenced by what they care about and what they hope for. The world is transformed by our human desires, what we long for, what pains us, what we want, and what we don't want. Desires that are deeply shaped by our faith traditions, our cultures, and our personal beliefs. We want to create a world that we feel at home in. It inspires us to rise above our current circumstances and imagine new possibilities. One of our major desires is having our basic needs met and improving our living standards. Medical knowledge helps to treat many diseases and improve standards of living. Imaging technologies such as ultrasound and MRI allow doctors to diagnose diseases in non-invasive ways, and biochemical knowledge allows doctors to learn a lot of information about our health from a simple blood test. Another major human desire is for ease of mobility from one place to another and to travel across large distances. The invention of the car and the airplane has made traveling much simpler and faster than in the past. And as more knowledge is acquired, the design of vehicles is improved, and they are made more energy efficient to minimize resource consumption. As individuals, we use scientific knowledge in day-to-day decision-making. Knowledge about germs will inform your decisions around hygiene. Knowledge about the sun, UV rays, and its effect on the skin will inform your decisions around wearing sunscreen. Knowledge about anatomy and physiology and biochemistry will inform your decisions about available medical treatments, etc. But science itself does not tell you what decision you should make. It just provides knowledge that you can use to help you decide, alongside other factors. There are many decisions that have been made at the level of society. Vitamin D is added to our milk because it is well established that a lack of vitamin D results in rickets, a bone disease. Highways are banked around curves to keep vehicles from skidding at high speeds. Wood and timber that are used for buildings are engineered to be more resistant to fire. Science provided the knowledge underlying these decisions, but it was human desire for community health, efficient transport, and safety that turned the knowledge into concrete actions. That is, societal decisions around the use of scientific knowledge are driven by value judgments, desires, and economic trade-offs, not science. The decisions a nation makes will be affected by its politics, culture, religion, and economics. But most importantly, using scientific knowledge to make decisions does not require us to sacrifice what we value as human beings, and the knowledge we gain through other ways of knowing is an important part of how we choose the world we want to live in and how we create the future. And also how we prevent the use of scientific knowledge in ways that are not helpful to humanity. Very often, it is scientists themselves who question the uses of technologies that can be developed using scientific knowledge. And I will provide two brief examples. Lise Meitner, I quoted her earlier, was a physicist who played a major role in the discovery of nuclear fission in 1938. Realizing the potential for it to do great harm to humanity through the development of atomic weapons, said, "I will have nothing to do with the bomb." However, the results of her research led to the development of medical imaging techniques and radiation therapy that are still used today. Ursula Franklin was a Canadian physicist who strove to educate society about the beneficial impact of science on quality of life and the health of communities. And her research and teaching were focused on that. She delivered the Massey Lectures in Canada in 1989, called The Real World of Technology. Though the lectures were given 35 years ago, much of what she says resonates with people today. It is important to note that her definition of technology is not a collection of gadgets or machines, but rather a system of organizational methods, procedures, and mindsets. That is, she was not against using technology, but rather recognized its many benefits for making our lives easier when the user has control over how the technology is used. However, she was a strong advocate for thinking critically about the technologies that we adopt in our society and being aware of the unintended consequences of them. Her particular concern was how technology affects the way that humans interact with each other, as she valued social cohesion and a deeply engaged citizenry. Ursula Franklin was also concerned about the effects of atomic weapons testing on the quality of human life. She was part of a team that performed an extensive scientific study on the effect of atomic testing, which began in 1945. The study showed that the teeth of Canadian children born in 1963 had 50 times more strontium-90, a radioactive substance that is believed to cause cancer, compared to children born in 1950. The results of this study contributed to discussions on nuclear weapons testing in the United States and the Partial Test Ban Treaty of 1963. This treaty involved 135 countries and banned all nuclear weapons testing in space, underwater, and in the atmosphere. Now I will conclude with a few additional comments about science and hope beyond practical utility. Like Kepler and Newton, many scientists approach their work out of a spirit of curiosity and a desire to understand nature, not out of a desire to control it. Here is another quote from Kepler. "We do not ask what hope of gain makes a little bird warble, since we know that it takes delight in singing, because it is for that very singing that the bird was made. So there is no need to ask why the human mind undertakes such toil in seeking out these secrets of the heavens." Similar to the way a painting or a poem might inspire awe and joy, the same can be found in studying nature. Furthermore, the scientific picture of the world changes our perspective on our own existence. As physical beings, the scientific picture shows us that we are just as much a part of nature as everything else. Science has revealed that there's a deep connection in nature between all things, from the large scale of galaxies to the small scale of atoms, and the chemistry of living things. The incredibly large scale of the universe and the intricate structure at the smallest sizes can make us feel remarkably small. However, the organization of nature across size scales can also make us feel that we are part of something much grander. Science reveals the beauty in complexity, and studying it is a way of finding meaning in the patterns that govern our existence. The wonder it inspires is a way to transcend ourselves and to find beauty and depth in nature, all of which enriches our lives. Thank you.